Welcome everyone. We're going to be working on the ultrasonic distance sensor today. So you're probably wondering what exactly it is that we're trying to do. You'll find an updated document that has all of these LEDs actually connected. So we have our outputs. We're going to be running from channel 5 all the way up through 13. So again, have our power and ground rails connected to the Arduino. You'll find the updated code files attached to the announcements. This will help make things a little bit more clear, and we'll get into some of what that involves. So some of you that did the pre-lab found the obstruction there, trying to prevent you from seeing exactly how the trigger and echo pins were connected. That was not for this class, that was for another class because they needed to complete this as part of their project. So this is what the completed project looks like. This is a remnant from what was called a social distance sensor back in the day. So what we have is we have a couple LEDs that are going to tell us something about the range. This one is a final LED that we put in as a death indicator. So what we have is a couple simple principles. We'll walk through some of the code here real quick to give you at least some of the sense of what's involved here. So this resets the trigger and echo pin to actually be 7 and 6. So it doesn't really matter which one's which, so long as you're keeping track of how things are connected and what code goes into the board. So these are the two numbers that are most important. So we have a couple variables that we create, and we set up all of our outputs for the LEDs and all of those other pins. We give a couple other names to a couple of these pins. So then we actually run the code. What we're doing here is we're starting everything out by writing the trigger pin low and then high. So we have a 2 and a 10 microsecond delay for a bunch of things. And what we're going to be doing is actually sending out pulses to this ultrasonic sensor. So it has a T and an R, and this is corresponding to the same exact part number that you guys have in your kits. So somebody who's good at engineering, tell me what the T and the R stands for. Time is a good guess. Any other guesses?
Traction.
Could be traction, right? Could be trajectory, right? What other T words can we think of? Tantrum, not quite, no. What else? Target, right? No, not quite.
Oh, no, just kidding. Wait, what's the one?
Just kidding doesn't start with T.
Period. Isn't that the symbol of capital T?
Not quite, not quite. We're getting closer. We're sort of asymptotically approaching an answer. If we have a T and an R pairing, this is something that's going to be happening a lot of times. If you have something like a remote, what do you also have to have?
Oh, some sort of wave.
Trigger.
Trigger, very close. A transmitter and receiver, good. Give yourself a pat on the back. There you go, transmit and receive. That's how it goes, okay. So transmit and receive are our two sides. So we know which side is giving the sound out. We know which side is receiving the sound back. So these round little circles, have you guys seen these before?
Yes.
Yes, you just have to think about where. Where have you seen these little circles?
Can you point to the little circle?
Yeah.
Those guys. Speakers.
They look like speakers, and they are.
Looks like Wally's face.
Any speaker is also a microphone, which is how the NSA is spying on literally everyone. It's fantastic. Okay. Where else have you seen them? Think about on the backs of cars. Bumpers, right? So what are they? Distance sensors, right? So this is the same kind of technology that's in the ultrasonic distance sensors that they use in parking. So there's a couple things that we can understand about how they work. The first is we need to have some kind of trigger. So the trigger pin is going to send the signal out. Then we're going to bring in on the echo pin. We're always going to be reading the echo pin. So we're writing different time lengths to the trigger and echo pins. Why there are those specific ones, don't ask questions you don't want the answer to. Just trust me that those are the correct numbers. So we're going to be listening on the echo pin, and then we have a distance equals, so this is a formula. This is how we're calculating something from the information that we're getting back, called duration, right? Because if a sound wave is sent from the transmitter, what's it got to do? Has to get to the thing, bounce, and then come back. So how many times does it have to cross that distance? Twice, right? So we divide by 2, because should be obvious, right? So then we have this number. Anyone know what that number is? It's obvious, right? It's a number. It's a constant. Do you know what we do as engineers? We hide our ignorance in constants. We just call them fancy things, and we say, trust me, it's 0.0123765. Why? Because how much time do you have? That's why. So what we're going to do is we're going to actually calibrate, because what you're going to find is this constant sort of slightly doesn't work for your specific system. So each of your individual sensors are going to be slightly different. So we're going to have to do a calibration. Now, if you guys are thinking about this, how are you going to do a calibration for this particular lab? What kinds of information are we going to get? We're going to get something about distance, right? What do we have out on the tables to help us with distance? We have the meter sticks, right? So we can actually set something a fixed distance away from the sensor and measure what it tells us, right? So if it's 29 inches away, and we know that, or if it's, in this case, we're going to be calibrating for it to read in feet because it's easier in feet. If we set it at 3 feet away and we measure the distance and it says 2.9 feet, how far off are we? A little ways, right? But somebody else's with the same constant might say 3.2 feet for that same constant. So what we need is we need to figure out the constants for each of these, right? So I'm going to demo what that's going to look like using this process where we're actually going to be using what's called a serial print over the serial monitor. So this thing that we've looked at before, we're going to look at the serial monitor that's going to give us back information about the distance, and then I'm going to pull in samples every 100. You guys remember what that 100 stands for? Milliseconds, right? So how many samples are we taking every second? So carry the 1. Anyone? So if we're taking samples every 100 milliseconds, how many samples per second are we taking? 10. 10. Yes, 10, because we're using 100 1,000ths of a second for each one, right? So it's a factor of 10. We ask these hard questions to make sure you guys are sufficiently caffeinated to actually be here today. So that's important.
Can you quick whisper those resistor values?
So the resistor values in this case are just the default resistor values, and these are nothing particularly special. And we're not focused on this secondary breadboard with the LCD readout because trying to coach you guys through those is a little bit more than is reasonably expected. So 1 kilo ohm is sufficient for this. In this case, I was being lazy with my circuit and ran everything across with a ground strap to a single resistor, which is fine. It may not be technically the correct way to do it, but it's the way I felt like doing it, so that's what I did, because I'm the boss, that's why. So now we have our if clause. So in the Word doc that was posted that has all the wrong information in it, all of this is missing. Now I could have done this with series and for loops and all kinds of other fancy things, but this is just straight simple code so you guys can actually see what's happening. So if our distance is greater than 10, all of the LEDs are set to a high position. So what do we expect the code to do? If all of them are set to high, everything that we're telling the Arduino thinks in terms of high and low, on or off, right? So in high setting, typically, that means that everything is turned on. So all the LEDs are turned on, except for the very, very last one. The very, very last one has a very special scenario for it. So then we go, and if the distance is between 10 and 8, then we say, all right, we're going to turn one of them off, and then we're going to progressively turn more and more of them off as the person gets closer. And so what you'll see, and I'll show you what this looks like in the demo window, because you actually can adjust the distance away from the sensor in the simulator. We progressively turn these off as things get closer, and so then at the end, all that's left is the red, and then at the very, very end, this is where life ceases because someone is too close, because they're probably in less than a foot of you, and you could see where that would be a problem. So personal bubbles are a thing. Remember to keep them in mind. That was a thing before COVID, so all right. Here we go. We're going to close this out so that you guys can see the simulation for a moment. And what we're going to do is we're going to see all of these LEDs illuminated, or most of them. They're not all illuminated right now. So this one should be, this one's illuminated. It's just a little more dim than a couple of the others, so it's probably been on too long. So we have a distance measurement for what it says, and it gives us both in inches and metric. And as things get closer and closer, we see these turn off. So if you're within someone's bubble, oh, you're within less than 4 feet, you're dead. So that's what the social distance meter told us, right? So it is what it is. Maybe just don't get within 4 feet of people. Keep life simple. And then bring this all the way back out. So what we're doing is we're going to be setting an object a certain distance from our sensor, and if we look in the serial monitor, we've got information. So we need to know, based on this, how far away are things? So 100 and somewhere about 108 inches, someone who's good at math, what's 108 inches? 9 feet, right? Carry the one. There you go. Something about 9 feet. So 9.01 feet, right? So what about if we bring that in a little farther and we do, let's see, let's do 72. Anyone's height exceed 72 inches?
That's 6 feet.
Couple of you, 6 feet. Good. So we should have some sort of a sense of how far this is and what the value should be. It's a little tricky to get exactly 48. We'll get pretty close here. So 48-ish, somewhere around 4 feet. So what we have to do first is for each of your individual examples, you're going to have to change this. So how would we do that? What we're going to do is in Excel, we're going to take the data from about 3 or 4 different distances, and we're going to plot what it tells us back in the serial monitor. So we're going to have the true distance, so the distance measured by our meter sticks. Then we're going to have, that's going to be one column of our data. Then another column of our data is going to be the measured distance. Then we're going to plot those against each other. We're going to fit that with a line. The slope of that line, what's that going to tell us? That's going to be this number. So velocity is a good guess, but when you plot distance versus distance, what you end up with is called a calibration curve. So it was a trick question because we did derivatives last week, right? So, but it's always a trick question in my class. So it's really scary to answer questions. So what we're going to get is a different value for this number. This number will be close. It'll be in the ballpark. But if we see that if we copy this number, and we add back in this distance, so if this was the original value, so 0.003 or 0.0343, we'll stop this, and 0.00343, 343. If we run this now, for the given distance, it shows 120, 121 centimeters. It actually is off by on the order of about a half a centimeter or so, and it varies a little bit more. So it's very hard to see how much of a difference there can be. So each of your individual sensors are going to be plus or minus some margin that is the quality control system right now with supply chain interruptions and all of the quality control from all the different processes. So we're going to have to reconfigure these numbers to fit better. This is going to be calibrated at least for this number in feet. If you want to do it in inches, what do you guys think you're going to have to do? You could divide by 12, and that would give you a starting point for inches, but the fastest way is just to measure the distance in feet here, convert it in the second column over to inches, and measure the distance in inches, right? Or you could do the sensible thing and do everything in metric. But that, you know, that's just a crazy idea I had. So, all right, what we're gonna do is go ahead and have you guys get started. You need to replicate this on your actual device. You're going to do the calibration process, get the slope of that line, replace this constant with it, and then we're gonna measure the velocity of these little toy cars, right? So they're not actually there for entertainment. We're gonna figure out how fast they go, and if it's constant, using the ultrasonic distance sensors. So that's where the derivative stuff comes in, right? Ready, set, go.